Hi, I'm AJ Boydston from the Department of Chemistry at the University of Washington. My research team focuses on the areas of polymer synthesis, functional materials, and additive manufacturing, also known as 3D printing. We do most of this with an emphasis on the study and application of polymer mechanochemistry. Mechanochemistry involves the use of mechanical force to facilitate chemical reactions. This area is particularly fascinating to me in that chemists and engineers are able to directly couple macroscopic physical deformations to molecular level distortions that drive chemical processes.
Let's consider a physical object that might have some engineering purpose. Here, I show an octet trussed unit cell, but it could be anything. You could envision impact-resistant armor, a helmet, an orthotic device. If we apply great enough mechanical load, nobody is surprised that the material will eventually fail, and we can even observe significant deformation and cracking of the material. But if this were an important structural component, we should consider how might we have known when the material was about to break? Or, if the damage was not as obvious as a large crack, could we have easily determined how big of an impact the material experienced if we weren't actually observing the time at which it experienced that impact? Taking it a step further, we like to wonder, are there ways we can avoid fracture or failure, for example through localized chemical reactions? And so for a chemist, the answers to these questions come at the molecular level. When you zoom in far enough, you can imagine a single polymer chain experiencing elongation as a result of the tensile load. In many cases, the tensile load can lead to fracturing of the polymer chain that would typically be a destructive outcome. However, chemists are able to re-engineer the molecular structure in ways that can lead to useful outcomes, such as a color change that can indicate the location and amount of strain in the material, or release of reactive molecules that can help mitigate the damaging effects of the mechanical load. In one instance, our research team has been able to integrate mechanochromic polymers that change color under mechanical load, with different types of 3D printing. The particular type of mechanochromic molecule that we used in our initial studies was first developed by researchers at the University of Illinois. By synthesizing and processing the material in a way that enables 3D printing, we were able to rapidly produce prototype force sensors in which the mechanochromic regions were placed at specific locations in the device. This allows for someone to analyze the sensor after it experiences a mechanical load and know what the peak load was simply by being able to see the color and counting the dots. Essentially, part of the load history has been quantitatively recorded into the material.